Hello everyone, my name is Konstantinos, and in this talk I'm going to present our work that aims to make existing database tuners faster by pre-selecting important nodes. This is a joint work with Ram and Shivaram. So let's start with some background first. Database systems are usually shipped with a default configuration, and you can see here part of the configuration file for Cassandra, and as you can see, it consists of a set of knobs and then some values, some predefined values for each of these knobs. Now, the tuning process is basically the process where we try to identify the optimal set of values to, for these knobs, such that we can achieve high performance. And numerous studies have actually shown that properly tuned database systems can achieve 2 or 3 times more throughput or lower latency when compared to untuned ones. However, tuning is a hard problem, and there are many reasons for that. In a typical system, we can find hundreds of tunable knobs, and most of them take continuous values, and also there are some unknown interactions among these knobs. Finally, even evaluating a single configuration is expensive, as it can take several minutes. So earlier tuning efforts basically relied on experience from database experts. However, most recently there has been a number of frameworks that can automate this procedure, and more interestingly, these can actually achieve or even exceed the performance level when compared to human experts. So let's look inside these tuners for a second. Most of these tuning frameworks actually consist of 2 phases, the offline profiling phase and the online tuning phase. In the offline profiling phase, the tuner will generate many thousands of configurations where it will tweak many database knobs for these configurations, and then it will evaluate all of them on many workloads and measure the performance that the system delivers. Then, using this data, it can actually either train a machine learning model or put them into some knowledge base for future reference. Then, in the online tuning phase, we fix the workload that we want to maximize its performance, and now we can reuse part of these already evaluated configurations in order to bootstrap the tuning process. Can take several hours. So it's worth noting at this point that the offline profiling phase is really vital for the quality of the proposed configurations, and you can imagine that this phase actually will tell the tuner some important things about the database behavior, right? However, this phase is very time consuming, and it actually dominates the entire tuning time, as it can take many hours to several days. So if we look a bit closer into this phase, we'll see that in the beginning we consider all tunable knobs, and also we evaluate the generated configurations on many workloads. So one question that we had is how many knobs do we really need to tune to achieve good performance? And also, if this set of knobs, where we will call them from now on important knobs, is small enough, how can we exploit this small set of important knobs to accelerate this offline profiling phase? So in this work, we conducted an experimental study, and we actually experimented with a single workload first, asking how many knobs do we need to achieve good performance. Then we extended our work on other workloads, and finally we experimented with a different database system. And very surprisingly to us, we saw that for Cassandra and a balanced workload, we see that we only need 5 out of the 155 knobs to achieve really good performance. And also these 5 knobs are also important for a completely different workload. Finally, we saw very similar behavior for a completely different database system, PostgreSQL, that actually makes us think that our observations for Cassandra can also generalize to other systems. So for the remaining of this talk, I'm going to present our methodology, our results, and then some future work on database tuning. So the methodology consists of 3 steps. The first step is the ground truth dataset collection, and in this step we basically generate and evaluate many configuration samples where we tune many knobs, and this step is very similar to the offline profiling phase of existing tuning frameworks. So at the end of this phase we end up with a dataset that consists of configurations and the performance measured for its configuration. In the second step, we put this dataset through a machine learning model, and the goal here is to identify relationships between each knob and the system performance. Now, the machine learning model that we use can actually give us a ranking of these knobs. So in the end, we end up with a ranking of the knobs, or a set of the important knobs. At the final step, what we do is we basically evaluate the performance of the configurations that only tune these important knobs, and then basically we compare the performance that we got from configurations that only tune important knobs compared to the ones that tune many knobs. So let's talk a bit more in detail about these first 2 steps. So in this first step, we want to basically generate and collect many configuration samples. And it's true that we're limited to samples because we cannot actually evaluate all possible configurations. Recall that the knobs take continuous values, so it's impossible to do so. So for this work, we use a method called Latin hypercube sublink, which will basically generate many samples inside a large dimensional space, and it will also ensure that this space is covered uniformly and thoroughly. So this method works as follows. We basically define the number of samples that we want to generate, and then we also provide the range of values for each sample. And you can see in this figure a very simple example for 3 knobs. And each of these points or configuration samples can look like this. So we basically take each configuration can take very different values depending on where this point in this large space lie. So the second step is that we take each of these configuration, and then we measure its performance on a real system, and we do that for all configurations. So in that, as we said earlier, we end up with a data set, and then we treat and then we use a regression analysis in order to identify which knobs are important. And in this work, we use a machine learning model called random forest, which actually allow us to look inside how this model was created in the first place and which features or knobs in our case are important. Note that each knob will take a specific importance score, and this score actually corresponds to how important the model believes that this feature is, and this also relates to how much of the performance can actually be explained by the values of this knob. So in order to evaluate these configurations, we use a typical hardware. We use Intel Xeon machines with an SSD, and we also use multiple machines to parallelize the evaluation process. And now, in order to generate the ground truth dataset, we consider 2 workloads, YCSB-A, that is a balanced workload, and YCSB, which is a read-heavy workload. and we generate 25,000 samples where we tweak 30 knobs for each system. So now let's see that the results that we got using the methodology that we described earlier. So recall that the first question was how many knobs matter, and in this figure you can see the importance score that our machine learning model assigned to each of these knobs. We can observe that only 5 knobs have really high important scores, and these knobs actually correspond to controlling the number of threads for reading operations, and also the number of threads for handling user requests, and finally some knobs that are related to the memory table behavior. So according to our machine learning model, these are the 5 knobs that actually affect the performance the most. But the real question is, how much performance can we actually achieve by tuning these knobs? So we run the experiment, and we actually pick the best configuration for each dataset that we generated. So the first row shows the performance that we got in terms of throughput, read latency, and write latency when we tweaking 30 knobs. And the second row is the performance when we only consider tweaking these 5 important knobs, right? And as we can see, we get almost identical performance in both cases. So it looks like tuning just a few important knobs can still yield really high performance. And that's a very interesting observation. And now that we are considering a different workload, our read-heavy workload, we see again a very similar picture. We see that again only very few knobs actually affect the performance for this workload, and more importantly, there is a significant overlaps of these knobs across these 2 workloads. Now we turn our attention to a completely different system, Postgres, and we run the same set of experiments. And as we can see, there is again some similar observations to be made here. However, the knobs are not exactly identical. There is a bit more diversity in the order of these knobs. However, we can observe that the top 8 knobs are almost identical, even in this case. So in this last part of the talk, I'm going to focus on how can we exploit these observations to make database tuning faster. So our proposal is to utilize a machine learning model to identify the important knobs before actually running the tuner. And our key insight here is that this will actually reduce the configuration search space of the tuners. So recall that the current design looks like this. The auto tuner will basically consider all tunable knobs, but our proposed two-level design is basically this, where we also add a step before running the tuner that identifies these important knobs, and then the tuner will only consider these important knobs for tuning. And some very early results using an existing tuner showed us that we can actually reach the same level of performance using 5 times less iterations when we only consider the top 5 knobs compared to all 30 knobs. So even though we have some very early promising results, there are still some very interesting challenges ahead. And one of the very first challenges is how can we make the pre-selection step cheaper? Recall that we actually needed to evaluate 25,000 samples in order to reach this set of important knobs. And after some very early results that we got, we were able to reduce this number of samples to around 400. But can we actually do better than that? Are there any other methods that we could potentially use that maybe do not use machine learning at all? Another interesting point is how can we actually identify the impact of hardware to the set of the important knobs. So if we actually conducted the same set of experiments into a cloud machine, then would the set of important knobs change? And if it didn't really change, or like there was a significant similarity between the important knobs, we can actually exploit that in order to minimize the time that the tuner takes to adapt to new hardware. And finally, can we actually account for system reliability when tuning? It is true, unfortunately, that the tuners might sacrifice reliability in their quest of reaching higher performance, and they often tweak knobs that can have very bad results. So what we can do about that? So in summary, in this work, we saw that tuning a few important knobs can yield high performance, and we saw that this trend seemed to hold across different workloads and systems. And we also proposed an initial design to accelerate database tuners. So thank you for your attention. If you have any questions, you can reach me at this email address below.